Also, I'd like to get your lab out. If you guys get your lab out, I'll take some questions on the lab. That is due tomorrow. Remember, we did the lab on Thursday with the long collecting tube. You collected around between 40 and 50 milliliters. Anytime. You collected between 40 and 50 milliliters of a gas, it'd be hydrogen gas, and then you have to go through a series of steps. Number one, you look at your lab. I'll let you guys get that out. Number one, what you had to do is you had to figure how many grams of magnesium you started out with using your length around 2.5 centimeters, and then using the conversion ratio, it says for every 100 centimeters you have 1.60 grams. You need to probably show more than one significant digit when you get an answer for number one. Okay, if you show less than what's needed, then there'll be maybe a half a point taken off. So make sure you're using significant digits correctly all the way through. Number two, you're supposed to take that weight and change it to moles of magnesium, right? So on that one, you've got the grams, you just use the periodic table, and you convert it to moles. Showing correct significant figures on that one as well. Number three, you're supposed to set up a chemical equation that indicates your reactants, which would be magnesium and hydrochloric acid, and your products as you get out. So that would be like a single displacement reaction. Look back at chapter 7 if you've got questions on that. We did a bunch of single displacement reactions, so if that's something you need to look back to just kind of review. You've got to write your products out. Remember, hydrogen gas that you produce is one of those genuine elements. They end in gen, so they have to be diatomic. So don't forget that. Write the states of matter that you have. If it's a solution, it has to be aqueous. If it's a gas, it has to be G. Okay? Number 4 is using Dalton's law of partial pressure. So turn it over. Dalton's law of partial pressure says, in this case, P total is your barometric pressure for the day. So when we looked at the barometer up here, that was your pressure. That's your total pressure in the room. The pH2 is what you're solving for. The pH2O is in your data table at the bottom. That's the one you looked up on in the appendix. So that is pH2O. You're asked to use Dalton's law of partial pressure, which you should have in your notes, to solve for how much hydrogen gas you have in there pressure-wise. That becomes your P1 in problem number 5. That's your P1 in problem number 5. So that's your initial pressure. Your initial temperature is based upon the temperature of your water, which would be on the front, but it has to be in Kelvin. And then your temperature is of the water, and then the volume of the gas would be what your reading would be in liters. Okay, you should have that on the front. So your beginning volume is the volume in liters, liters when you converted it. Some students are converting, in the last class was converting milliliters to liters incorrectly. They were dividing by a wrong number to get that answer. So make sure you're looking up the conversion, make sure you're doing it right. Okay, your new conditions are at STP. So the new conditions, pressure and temperature, are at STP, these bottom two. But you won't use ATM, right? You're going to use KPA, right? So you'll have to know standard condition in KPA what it is. And you can plug that in for your ending pressure. Your ending temperature is here too. So then you get a volume, and it should be less when you calculate it, it'll be less than your initial volume because the temperature is going down and the pressure is going up. Both of those together will cause us to have a lesser volume under those new conditions. Cooper?
So is STP, is that your number for volume 1? And
No.
temperature 1?
No.
That's your ending?
That's your ending.
Okay.
Yep.
Same with pressure?
Yep.
So it's all that. Second.
Yep, they're all second because we want to get it in a condition so we can solve for this number here, 22.4. So everything should come out to where we come up with an answer in the 20s somewhere. Okay, 20-something liters per mole when you get your final answer. Okay, and that would be the answer you're coming up with on number 6. Number 6, if you want to write down the answer, I think it says what the answer is supposed to be, right? Number 7 it does. And then you find your error. Now your percent error, all you have to do is take the difference. So if I came up with 25.0 is my answer, then I would take 22.4 minus 25. I get the difference. The smaller the difference, the less percent error I have. So I would take the difference between those two, which would be 2.6, and then I divide by 22.4 times 100. So I always divide by what I should get. The difference divided by what I should get times 100. And that gives me how far I'm away from the true answer. What the answer is supposed to be, based experimentally anyway. Okay? So you guys can work on that the last 20 minutes of class. We'll give you time to do that. The other time, there's 5 questions you're going to do for tomorrow. I'll put them on the board at the very end. But we're going to go through what's called the ideal gas law real quick. We're introducing moles. We've had pressure, volume, temperature. Now we're introducing moles. We've talked a little bit about molar volume. That's the volume that you would get if you had 1 mole of gas at STP. You'd have 22.4 liters. So, okay, on the board, you opened up to a page in your book, page 379, that if you look off to the right-hand side, they give you 3 different gases that are all under conditions of STP. And if you count the number of molecules in their samples, they take just a small sample, it's going to be the same every single time. Hydrogen's the lightest gas, oxygen's a little heavier, and then CO2 is just a little bit heavier. So off to the side you got a purple balloon, yellow, and blue. And if you take the same amount of volume in the 3 balloons and compare them and count the number of molecules, they'll be the same. So that's what Avogadro law says, that if you have equal volumes of gases and they're all at the same temperature and pressure, they're always going to contain the same number of molecules. Always. So the number of molecules in this box represents 1 mole of molecules. And that's called a molar volume at STP. So this would be conditions under standard temperature and pressure. The volume is going to be 22.4 liters. That's your volume. Okay? And so we're going to use this here in a second to solve a problem. And we'll talk a little bit about that problem, what it is here in a second. But these are conditions that are specific. They're 1 mole of gas. It's always nice to look at comparisons between 1 mole of anything, and that's 22.4 liters that you'd have. Okay. I'm going to go ahead and move to the next screen here in a second, which gives you that number. So you want to write down molar volume at STP is 22.414 liters per mole. You can do that because that's what the next screen would be. Okay. So put that in your notes that anytime we have 1 mole of a gas under conditions that are standard temperature and pressure, that we'll always get a particular volume or constant volume, and that's 22.414. Okay, so the only thing we haven't calculated yet, that when we look at all these laws, would be the number of molecules. And we represent that in moles. So the only thing we haven't done, we've figured pressure, volume, temperature, we've done all those. The only thing we haven't looked at has to do with moles. Okay, and what moles are. So to do that, we're going to use the ideal gas law. Okay, so the ideal gas law we're going to use is, we're going to look at it here in a second. The word description of it, it says, at any point in time we can compare mathematically the relationship between 4 variables: pressure, temperature, volume, and moles. Is moles. So anytime you see the symbol N from now on, it's going to, you're going to have to put the number of moles of molecules that you would have. So, like always, that mathematical relationship we're going to go ahead and give you. There's another symbol that we're going to have to calculate. We're going to have you calculate that here in a second. And the symbol is R. Okay? It's a capital R, and it's the ideal gas law constant. Okay? And we're going to have each one of you, based upon these numbers right up here, find the R value based upon the pressure that we're using at the time. Now, I need to tell you that pressure can be in, this pressure can be in any pressure. You could have it in ATM. You could have it in KPA. You could have it in torr, or millimeters of mercury. Need the same thing. Temperature has to be what?
Kelvin.
Kelvin. Volume has to be, when you use this law, has to be in liters. You have to have it in liters. And of course, N would be moles. Right, so the only thing that will change when you use this law is your pressure, depending upon which pressure you want to use when you're plugging in to solve for volume, temperature, moles, any of those quantities. Okay. So we usually think of a constant as one number. What's that number? It never changes. But we're going to have 3 R values because it's going to be based upon, do we plug in torr? Will we plug in KPA, or will we plug in atmospheres? It really depends. Our R value changes due to our pressure that we're using. Okay. If we use atmospheres, it's a certain R value. If we use KPA, it's a certain R value, and so on and so forth. Okay? So this is what I'm going to have you do, is I'm going to have you solve for R. The whole class is going to solve for R. I'm going to erase this answer here, or scribble through it. Alright? This is the ideal gas law equation. You want to write that down. This will be given on your test, where you have to use the ideal gas law to solve. And it says if you take the pressure and the volume and get the product for that, it will always equal the moles and the temperature times a constant, R. So what I've done on this second part is just switch the equation around to find out what our R values can be, depending upon their pressure. So remember, pressure could be in units of atmospheres, we could use KPA, or we could also use millimeters of mercury. So any of those, depending upon what we're given and how we're plugging it in, we could use any of those. But then our R value will change due to which pressure we're
What's the
using.
R value?
Okay, we're going to find that out.
Okay.
Glad you asked, Cooper. We're going to have these two rows here. You're going to get together. You're going to do it individually, get together. And you're going to set up your equation to solve for R. And you're going to use these values up here on this box. So the moles you're going to use what's on there. Your temperature, you're going to use that temperature. The volume, you're going to use this volume that's on the box. And then what you're going to use for the pressures in atmospheres. So you guys are going to use exactly what it says on there. You plug those numbers in to R equals PV over NT, and you'll come up with a number, and we're going to look at it. The middle two rows, we're going to have you use kPa as your pressure. So the only thing that's different from the first two rows and the middle two is you're plugging in standard pressure in kPa, not atmospheres, for your pressure. Last two rows, what you're going to do is you're going to plug in torr as your standard pressure, which is 760. Middle two rows, standard pressure, kPa is 101.3. First two rows, standard pressure is whatever's on the box, 1 atm. Okay? You guys go ahead and calculate that, and we'll write them up on the board, the R values, depending upon the pressure that you're using. I can plug it in, the 8.31 for my R value when I do the calculation, and I'll get kPa as my answer. Or I can always use 0.0821, get it in atmospheres, and then convert it later. Does that make sense? So I could go, I don't want to mess with, I don't remember what kPa is and torr is. I always remember atmospheres. Plug it in, I get my answer in atmospheres. Or, they might give you a value in kPa, but these will be always given to you on the test. I'll have a section at the top that says these are all your R values. And you go, I need, that problem's in kPa, I want to use 8.31, or that problem has the pressure in it in the atmosphere, I want to use that one.
So those are the set R values
for those three different pressures, depending upon which pressure you're given. So the very first problem you're going to do, you'll have to determine which one you're going to have to use based upon the question and what it's asking. All right? So we'll do one problem. I think that's all we need to do, and then you'll do some practice. Turn over to page 385. Page 385 in your book, and we're going to look at practice problem number 1.
Can you view it here real quick?
Yep. Okay, so we're going to do practice problem number 1 real quick. Want to get done with this so you guys can have some time. I probably went a little bit longer on my description of the lab just because if you had that out and was going through it and kind of see if you were doing them right or not, that's due tomorrow. We're going to do one of these problems. And what's that problem asking you to solve for?
The pressure.
And the pressure. So if you look, again on page 385, number 1, it says, what's the pressure? But it specifies the pressure it wants the answer for. In atmosphere. So which one of those three are we going to use?
The first one.
Top one. That's our R that we're going to plug into our equation. Okay? It also gives us a volume in liters. It gives us a number of moles. And it gives us the temperature in Celsius, which we'll have to convert to Kelvin, like we always do. So, PV equals nRT is the equation we're going to use, and we're going to solve for pressure. So go ahead and solve for pressure, or come around and check your answers. After we're done with that, then I'm going to give you an assignment that has 5 problems to do for tomorrow. And you can work on your lab or the problems or both, depending upon what you need to get done. Alright, so that problem is asking for pressure in atmospheres. So we set up the symbols. P equals nRT over V, because we divide both sides by V. So then our moles is 0.325. Our R value, it asks for in atmospheres, and so we look at table 2, or the ones I give you. The one you need to use if you want pressure in atmospheres is 0.0821. I didn't write the units in there. You don't have to either. The temperature is in Kelvin, 308, and the volume is 4.08 liters. It has to be in liters. So you'll have some problems that'll give you it in milliliters, and you have to get it in liters. Because if you don't, this answer would be 1,000 off. So this answer is 2 atmospheres, I think. If we would have plugged in 8.31, we would have got an answer in kPa. If we would have plugged in 62.4, we would have got an answer in torr, or millimeters of mercury. Okay? So it depends upon what they want or what they give you in pressure. Figure out. So the problems I'd like you to do for tomorrow, and it is a completion grade. Get them done. I'll come around and check them, then we'll go through the answers. These first 2 are not ideal gas law problems. These first 2 is I want you to practice, since we haven't done much with the combined gas law. So 265 and 273 are not what we did today, but what we did, say, last Wednesday. And also on your lab, you're doing it on question number 5. Okay? 277 A and C and 278 deals with the ideal gas law. The one we just did. So that's on page 897. There's 5 problems doing for tomorrow. Work on your lab. You guys have about 15 minutes of time to work on those things. Okay? All right.
This is due tomorrow then?
Mm-hmm. I'll put it back.
Oh my gosh, thank you so much.